So I'm Ilana, this is my coworker Avikam, and we are software engineers at WeWork. And we will take you through basically a real-life architecture review of how to solve a real problem that we had with the way that we were previously using our RabbitMQ stack at WeWork. Oh yeah, fun fact. I am in one of 3 sets of twins in my immediate family. So I am a twin, and I have 2 younger sisters who are twins to each other, and also my dad is a twin. And we have come up with an even funner fact about Avikam since the slides were made. So Avikam is one of 4 people who has his name. So
It's
very
not
fun
entirely
fact.
correct, but it's almost correct.
Yeah, well, yeah. Awesome. Great. So what do? We are software engineers on the memberships team at WeWork. And what does that mean? It basically means everything related to membership management. So getting a membership which will let you book offices, any other type of space, adding people to your membership so that they have access to book space, anything similar to that, our team deals with. And we have a microservice that keeps track of all of these membership states, and different services publish their events that our service listens to. And you can see right away where this might go wrong, especially with how we used to think about how we would organize all these events. So we used to think, like, just make everything asynchronous. Like, obviously, like, that's the way to scale, right? Just make everything asynchronous. But you can see on the bottom, what if we get an event to add one office to a company, and then right afterwards we get another event telling us to add 2 people to that office. And adding 2 people is a very quick operation, so that might complete before adding the office ever actually finished if they were picked up by 2 asynchronous workers. And this actually did happen quite often, leading different accounts to be in incorrect states. So an engineer would have to manually go in and fix it. And that was taking quite a lot of developer time, like staring at messages, being like, where did they get out of sync? So it was very manual and very annoying. Oh yeah, and a little disclaimer here. This is all real, and we're going to be showing you real architecture diagrams that we made in order to try to solve the problem. So if you see the word Pegasus on it, that is our memberships API, which is the main system that we're going to be talking about. And if you see the name Spaceman, that is our reservation service. Cool. Yep. So we're not hiding anything from you guys. You're getting the raw slides.
Right. This is an excerpt of our code that is here to demonstrate kind of like how our code evolved into separating the consumption and the produce of these messages. So at the beginning we had everything processed in like the same monolith, like that space service would handle all of these things from within. We later transitioned into having this microservices architecture, and then we would hit our like little services, and all of these things would have been coupled, and we gained that synchronism just by having these things like processed in a very coupled way. So as we kind of evolved, we separated all of these tasks into RabbitMQ, and we decided to process everything asynchronously. And as we evolved even further, these micro tasks, so like these messages became smaller and smaller with smaller responsibilities, like just add space or just add person, which is a good thing because it's easier to maintain this kind of code. But when things need to be actually coupled, this is when problems actually starting to surface, and that's what kind of gave birth to the problem that was just described. Ilana is now going to kind of like present ideas that we hashed out to solve this problem. But one thing that I think is important to keep in mind is that we really wanted to solve it from within our domain. So it could be argued that we could go back, transition back into like just making everything like, very like tightly coupled and like, performing these calls synchronously. But that would defeat the purpose, like having these things like, separated. And also going forward, we cannot really control other services. So you could, just like, you can go on.
Great. So what is the simplest thing that we could think of in order to try to solve our asynchronicity problem? So the most naive thing that we could come up with was only process one message at a time. Clearly, our events cannot get out of order if we're only doing one thing at a time. So this is a real diagram that we made in order to work through the solution. And we're using Redis as a sort of distributed block. So the idea is we would basically push a key into Redis being like, yes, we are busy right now. And then if a worker came in to try to do work, it would first check to see if any other account was having any work done to it, and if so, it would wait. And we rejected this idea for a few reasons. First and foremost, it really doesn't scale at all. As you can clearly tell, we can only process one message at a time, so it's a little bit too naive. And also, it has all of the problems that are sort of inherent to distributed blocks. So what if a worker that came in and took the lock died before releasing the lock? Obviously, that's a solved problem, it happens all the time, but we're just two software engineers on a business logic team, so we really did not want to have to deal with that or spin our own solution to that. So we decided for a few reasons that we were going to reject this idea off the bat. And our second solution is basically a more complicated version of the first one. So instead of only processing one message at a time, we would now just sort of lock accounts instead of just locking the whole system. So we would push account UUIDs into Redis, and if any work came in for a particular account, we would lock that account before allowing any more work to be done on it. And this does actually scale way better than the first solution that we presented. So it is better. However, it still has all the problems that are inherent to distributed locking. And also, it's just way too complicated. You can tell just by looking at it that it's like a complicated solution for a very simple problem. And we really didn't want to have to build all of that ourselves.
Right. So to be able to get rid of a lock, we came to sort of a realization that we are willing to process for a single account one message at a time, but we really didn't want to give up processing multiple accounts at the same time. So the third idea that we talked about was having a queue that was designated specifically to an account. And then essentially when a message would come in from whatever publisher, our membership service would parse that message, understand to which account does it belong to, and then republish it to a specific queue that has only one consumer for that account. This also raised some concerns. One of the most obvious ones is that we could potentially have infinitely many queues because we cannot control the number of accounts that we have or the different messages that are sent to different accounts. So that was one problem, and we thought about solving that problem with just removing queues that are empty. So thinking about implementing something of a sort of a transient queue, which is also a concurrent issue, how can you guarantee that no message is in a queue before you decide to delete it, right? It's not an atomic operation. I think we can go on.
Cool. So what did we think of that solution? We liked that it didn't have any locks, like Avikam said. We liked that it is pretty highly scalable. And we liked that it could process multiple accounts at the same time. But the only real problem with it is that it wasn't simple at all. So much the same as the second solution, it's a little bit complicated to talk about and explain, and we thought we could do better. We only really get like 2 requests per second, which is really not that much, and we did not need a very complicated solution in order to solve our problem. So we thought, what if we could modify it instead of having like an arbitrary number of queues? What if we had a fixed number of queues instead? And this brought us to the solution that we actually ended up going with.
Right. So in order to achieve that and to get rid of like the transient queues that are popping up and going down, we decided to have a fixed amount of queues, and then a way for us to kind of like understand to which queue do we want to republish a message was just to use like a hash function on the account. That would guarantee that messages for the same account will always go for the same queue, and we could always also process multiple queues at the same time. Yeah, you can go.
Yeah, we have kind of like a sanity check for walking through it. So basically, like a message comes in from the reservation service to add a couple members to account ABC. And then we can see that the first letter of the account is A, which always maps to Q1. And Q1 only has a single synchronous worker pulling from it. And then, so that when a message comes in to delete 2 members from that same account, we see that the first letter of the account is still A, which still maps to Q1, so it gets processed in sequence because Q1 only has 1 worker pulling from it, and it's all synchronous now.
So all of this idea is kind of hinged on the fact that we can guarantee that there is only 1 worker per queue. And in order for us to get this guarantee, we really needed to exploit or use RabbitMQ feature of exclusive consumers, because we thought about cases where workers could die. So in order to overcome that, we created some sort of a background job that would constantly poll the broker and ask it, how many consumers does a given queue have? And if the answer was 0, we would spin up another queue. This is also a potential concurrent issue, because what happens if, for example, for whatever reason, we decide to spin up 2 consumers? So for that exactly reason, we're really happy to use the exclusively consumed queue flag, so that RabbitMQ would promise us that that wouldn't occur.
So the question that actually matters is, did it work? And I'm happy to report that it really did. So this is a graph over time that we pulled from Datadog, and the wavy line basically means that messages were not successfully processed because there was a problem with accounts. And then that sharp line in the middle, which you can kind of see, is our deployment, where we released our solution. And then you can see right afterwards, accounts got way more stable, and messages were beginning to be successfully processed every time. In fact, the reason why there are so many misses, I think, is because we still had to like rectify accounts that were messed up from the previous architecture. But after we did that, things were way more stable. So even though we're great, we're awesome, we solved our problem, everything is great, I don't think that we did everything perfectly. We probably should have tried a few more things first. But like Avikam said, we were very adamant that we wanted to solve it within our team, with the knowledge we had, and like do things that we could maintain easily. However, there is apparently a RabbitMQ plugin called consistent hashing that basically does what we described. We didn't vet it, so we can't promise you that it solves the problem, but apparently it does. And also apparently our solution is a lot like Kafka, with like the distributed like hashing key. We didn't really use Kafka a lot at WeWork, so I can't tell you if that is true or not, but we probably should have looked into these technologies a little bit first before just deciding to roll our own solution to the problem. So what we really want you to get from this talk is less is more. sometimes you don't need the most complicated solution to a problem, and if you can't describe it very easily, chances are it's too complicated, and you should roll back a little bit. But even if you are using a simple solution, you can still use cool RabbitMQ features like exclusive consumers. So we're really able to leverage the technology that we knew how to use in order to solve our problem.
Now with exclusively consumed, it should be even simpler than that.
Yep. And it looks like we're having a quality issue with one of the dogs, but yeah, that's Avikam's dog on the left, and that's my parents' dog on the right. Just telling you guys goodbye, and thank you for coming to our talk.
Thank you so much. So we have a few minutes for questions. Well, I can start. Can you tell us a little bit more about your team?
Yeah, like we said, we're software engineers at WeWork on the memberships team. We work together on this issue, but there are, I think, 6 software engineers altogether on the team, 1 team lead, 1 PM. But at like the core, we're a business logic team. Unfortunately, we don't get to just like solve cool architectural problems all day, every day. Like we do it in service of a lot of business logic. But I have the feeling that a lot of software engineers do that. So we were excited to give you a real life example of how just like thinking about what you really need and also what you don't need could solve your problem.
Yeah, so about Kafka, there are a lot of similarities, but it's a bit of a mixed bag. With RabbitMQ, what's nice is that you decided you had 2 events that you wanted ordering, and so with RabbitMQ and the consistent hashing exchange, you can get ordering of any events you want and put them through the consistent hashing exchange. As long as you use a routing key, say account number or whatever, they'll always go to the same queue. And that's very much like how Kafka works, but with Kafka you've got a bit more complexity because the topic is a shared resource. So, maybe you've got 2 topics and you just can't get your relative ordering of those 2 events, whereas you can with RabbitMQ because you get a lot more decoupling. So with Kafka, you actually have to make a decision, we need to mix both events into the same topic, and now that affects all publishers and all consumers of that topic. So they are very similar, but RabbitMQ does give you a bit more flexibility because each consumer can decide which events do they want relative ordering of, whereas in Kafka, it's an architectural decision that everyone has to get together. So it's just something to take into account.
Thank you.
Yeah, thank you. Yeah, appreciate dropping some knowledge bombs.
Thanks for a really interesting talk. I'm just wondering if you guys have any strategies for if there are certain accounts that are busier than others. Perhaps some accounts are not changed very often while others are changed very often. If you have ways to allocate resources to those busier accounts.
Yeah, thank you for this question. I think that the main strategy that we thought about scaling issues was, or I would say it otherwise, we thought about these kind of things as a scaling issue. Like, what if we want to kind of like clean up queues faster, or things like that. And to that end, we could just increase our hash. So our hash is literally like, modulo the number of queues that you would want to have. And if you want to saturate the messages across multiple, like more queues, you would just increase that number, right? And for specific busy accounts, I don't think we ever encountered that.
We never encountered specific busy accounts, but we did realize that our distribution of account UUIDs was not really random, and they did tend to like cluster. And I feel like if you knew in advance that some accounts were busy, you could like hash them to their own dedicated queues. You might not know that in advance, in which case you'd have to do something more complicated. But like Avikam said, you could scale in general just by like having more than, we had 5 queues, but you could scale that up to like quite a bit more.
Thank you.
So you said that you find out about the consistent hash exchange plugin late in your study. What would have helped you to figure out this plugin earlier?
Do you want to take it?
Sure. I mean, so we, I guess like it was not readily available when we like Googled the issue on, like quite frankly on like Stack Overflow. Like we only found out after we were kind of more in the domain of RabbitMQ a little bit more. Like how did you actually discover that it existed?
We just had some talks with like more engineering, like but further down the line, like when this project like gained more and more visibility, so like more people kind of like knew about it, and then it was flashed out.
Yeah, so I guess someone actually ended up telling us about it, but we didn't see it on the internet, and I think that like many software engineers, in order to solve problems, we just turn straight to Stack Overflow, and if it's not some of the top resources you see, it's like hard to find it.
Okay, thank you.
Thank you
All
very
right,
much.
thank you, everyone.
Thank you so much.